Hi, welcome to my lab on calculating the mass of a black hole. For this lab, we were given position data randomly generated from a seed of a star and asked to calculate the mass of the black hole affecting it. We're assuming in this lab that the only force acting on the star is due to the gravity generated by the mass of the black hole. We also assume that the black hole is located at the origin. Now, the fundamental principles we're going to use here are Newton's second law, i.e. that F net is equal to delta P over delta T, and Newton's law of gravitation, which is that the magnitude of the force due to gravity is the universal gravitational constant multiplied by the two masses involved divided by the magnitude, the distance between the two objects squared. So, the first part of my coding was to set my seed, set my initial variables and constants to the appropriate numbers. So for delta t, we have, I think this is the time in 1 day. For t initial, we just have 0. For the mass of star, we have what we're supposed to have. And for g, we have the universal gravitational constant. I also had to initialize some things before our loop. I'll explain what this av sum is a bit later. Now, here are our calculations. This is quite a meaty slide. So, obviously, we're calculating our P initial and P final using our V initial and V final, which is quite straightforward because you're just multiplying by a scalar there. Our change in V and our change in P are also quite straightforward. It's final minus initial. And then obviously delta P over delta T is delta P over delta T. All this is very uncontroversial. A lot of these are very, very characteristic equations. They're not, you can see the calculations here, but for instance, F net magnitude is equal to the magnitude of dp dt. That's just a fact, but here we are calculating the perpendicular and the parallel arrows. Momentums and forces. The really important calculation in this loop, however, is our calculation where we determine the mass of the black hole based on this data. So obviously, we want to calculate R, which is equivalent to the star's position, because the black hole is at the origin. Sorry. Then we square that, and we use that based on the gravity equation, which I've listed here. We rearranged the gravity equation to arrive at this equation for the mass of the black hole at the bottom. And we use that to calculate the mass, and then we print it, and we add it to average sum. Now, I'm going to skip to where I explain the average sum. So, the reason I'm averaging the mass of the black hole is because it's oscillating a tiny bit. It's moving around a bit because of some quirks in the code, which is explained in this campus wire post, and they suggested that we just average it, and that's what I did. And you can see the average I reach at the end over on the bottom right hand corner, and you can see how I'm doing that. I'm just adding to this sum, and then I'm dividing it by the count at the end. Now, here's the visualization at two different stages, and you can see I'm drawing these arrows, which are showing us the parallel and perpendicular forces. Now, the perpendicular force is basically 0, and that is because almost all of the force is actually, the parallel is basically 0, because almost all of it's in the perpendicular direction. And if I set my arrow scale high enough that you can see the parallel force, the perpendicular force is just ginormous. So I'm sorry about that. But here's how we're visualizing that. And it makes sense that the parallel is infinitesimally smaller than the perpendicular in this case. Now, for our conclusions, well, the first one's quite straightforward. Rate of change of momentum and net force are mathematically equal, but conceptually they are different things. The amount the momentum is changing is not the same thing as the force. Me pushing on something is changing its momentum, but it's not like forces are changes of momentum. So that's the difference there. That one's relatively simple in my opinion. Now, the interesting question here, what if we have a different black hole of a different mass in the same location? Would we be able to find out this new mass? In my opinion, yes. Because although we'd have to, the trajectory of the star might be weird, but we can still calculate the change in momentum at each time step and still figure out the force from there. There's no reason why not. The different mass of the black hole changes the force on the star, which changes our momentum changes. And from those momentum changes, the position data that we'll get will be able to tell us these, and we'll be able to work backwards. So there's no reason why we wouldn't be able to figure this out. Just some last notes that I really appreciate if you read. To add to this, I have come down with a cold, and I'm sorry if that's made my speaking harder to hear.